In this work, we present a probabilistic framework to resolve ambiguities in the spatial locations of photon incidences using multiplexed readouts from single-photon detector arrays. Single-photon avalanche diodes are widely studied for use in applications like LiDAR for self-driving cars, VR headsets, and smartphone imaging. However, they suffer from poor detection efficiency outside specific wavelengths. Detectors based on superconducting nanowires are lucrative alternatives to SPADs due to advantages like low dark counts, low jitter, high timing resolution, and near unity quantum efficiency across a range of wavelengths. Meandered nanowires are cryogenically cooled and maintained in a state of superconductivity. The detection of a photon results in a resistive hotspot that causes a voltage drop across the circuit. As the hotspot dissipates, the circuit returns to a state of superconductivity with no voltage drop across the ends of the meandered nanowire. Implementing arrays of SNSPDs for conventional imaging is challenging as the heat load associated with reading each pixel is incompatible with the cryogenics of the system. Row column multiplexing, where each row and each column is read instead of each pixel, has been used to realize kilopixel and megapixel SNSPD arrays. With row column multiplexing, if photons are incident along the same row or along the same column during a readout, or if a single photon is incident across the whole array, readouts can be mapped to the spatial locations of their incidences unambiguously. For example, if row 2 fires and columns 1 and 4 fire, we can infer the spatial locations of photon incidences as row 2 column 1 and row 2 column 4. However, when multiple photons are incident on the array at different rows and different columns within the period of a single readout, their spatial locations are ambiguous. For instance, if rows 1 and 4 fire and columns 2 and 3 fire, the readouts can be mapped to any of the spatial locations shown arising from detecting 2, 3, or 4 photons. Note that saturation results in multiple photons detected at a pixel being indistinguishable from a single photon detected at the same pixel. Thus, signal reconstruction from row column readouts is an ill-posed problem. The central question we address in this work is, can ambiguous readouts be processed such that imaging at high incident fluxes and with few measured frames can be realized? We consider an n by n SNSPD array acquiring multiple binary frames per measurement of the ground truth. Each frame results in a row readout vector and a column readout vector, which are used for reconstruction. Traditional methods either discard ambiguous data entirely, resulting in high variance, or introduce a high positive bias due to misattribution of photon counts to pixels. Our objective is to develop a method that uses most of the measured data to produce a low bias, low variance reconstruction. We now develop the proposed multiphoton estimator mathematically. If lambda is the spatial intensity distribution of the ground truth, the number of photons arriving at a pixel at time t can be modeled as a Poisson random variable. Each pixel saturates with the detection of a single photon, and we estimate the detection probability, which can then be mapped to the intensity estimate at each pixel. With full addressing, the maximum likelihood probability estimate is the fraction of the total frames with a click at the pixel. Row and column readout vectors are defined as indicator functions denoting a detection at each row and at each column. We derive the likelihood function for row column readouts and use it to calculate the Fisher information. The non-convexity of this function makes the ML estimation computationally intractable, and we therefore seek an alternative whose performance is close to the Kramer-Rao bound. The multiphoton estimator uses initial probability estimates obtained from unambiguous data to approximate the ML estimate. It attributes a fraction of ambiguous frames to each multiphoton event based on its probability. Consider the unique photon events in a 2 by 2 array. Events E0 through E8 are unambiguous and produce distinct readouts, while events E9 through E15 are ambiguous and produce the same readout. The probability of each of E9 through E15 can be computed as shown in the example, which is then used to find the conditional probability of each of these events given an ambiguous readout. The probability estimate at each pixel is computed as the ratio of the sum of unambiguous frames and an estimate of ambiguous frames with a click at the pixel to the total number of measured frames. A 2-photon estimator has terms for events E9 and E10. A 3-photon estimator has terms for events E9 through E14, while a 4-photon estimator has terms for all events E9 through E15. And since this is the general case, we refer to this 4-photon estimator as the multiphoton estimator. Here are reconstruction results for 32 by 32 arbitrary ground truth images with 100 Monte Carlo trials, 100,000 frames per trial and at a constant flux of 3 photons per frame, we see that the multi-photon estimator achieves a significant improvement in the peak signal-to-noise ratio of reconstruction over the traditional methods. We simulate the dependence of each of these estimators on the incident photon flux. The 4-photon estimator achieves the lowest MSE at a higher incident flux compared to the other methods, and the estimation improves with each modeled photon. We also show that the multi-photon estimator achieves a target reconstruction MSE with 4 times fewer frames compared to traditional methods. It also matches the Kramer-Rao bound closely across a range of incident flux values. Finally, we show that this method improves with an increase in the number of pixels in the array and can enable high flux imaging with larger arrays by resolving a greater number of coincident photons. Thus, we introduce a novel method to enable high flux, high resolution, and low latency imaging in single photon detector arrays with multiplex readouts. The method matches the Kramer-Rao bound across a range of incident flux values and can be extended to other detector types and multiplexing architectures.